Welcome everyone. I'm Norman Wahlberger. We're here at the University of New South Wales. This is a course in algebraic topology, and today we're going to talk about how to compute homology. So we introduced this idea of homology groups for a topological space. So X is some kind of space. And let me remind you what the setup was for homology. So we basically had this sequence of groups, and we call them chains. And I guess the zeroth chain on this side, so this is zero-dimensional chains. And then we had one-dimensional chains, and so on. Maybe three-dimensional chains. And we had maps between them called the boundary maps. And we'll call that one maybe delta 1, del 1, del 2, del 3. And although we didn't talk about it too much, we could also sort of extend it to one more map to 0. So this del 0 is just the 0 map, which sends everything to 0. So we have also two-dimensional chains or cells, like little disks, and three-dimensional chains, like little solid balls. And conceivably, we could keep going in this direction. Okay, and the crucial property that we established that the operator del squared equals 0. And what that means is that if you start anywhere in the diagram and you take some element, say in this group, and you perform the del of it, and then you perform the del of that, you're not necessarily going to get 0. The combination that you're going to get is going to be 0. So it's this identity, I guess, that drives the definition of homology. So how do we define the homology? Well, at every stage, we're going to have a homology group. So for example, around here, if we look at the one-dimensional chains, there are sort of two questions that we can ask with respect to these boundaries. The first is, what is the kernel of D1? So the kernel of del 1 is a subgroup of C1, and it's those things which get sent to 0 under the del 1 map. And that's usually called the cycles. So say Z1. This is the group of cycles. And it's contained inside C1. And then another relevant group is what happens from on this side. So if we look at all the two-dimensional chains and look at their images, that's also going to be a subgroup of C1. So the image of del 2, that's also going to be sitting inside here. That's usually denoted B1. That's called the group of boundaries. That's also in del 1 chains. And this relation here tells us that if we start with something in here and we apply the del to get a boundary, then if we apply the del again to that, we're going to get 0. So that's telling us that the boundaries are always inside, actually form a subgroup of the cycles. If something is a boundary, then it is necessarily a cycle. Something is a boundary here, it means it's coming from something over here, and that means that if you apply del a second time, you're going to get 0, so it means it's a cycle. So the boundaries are inside the cycles, and then it's the relationship between these two groups that generates the homology. So then we define H1 to be the quotient of the cycles over the boundaries. It's a quotient group. The homology is a quotient group. So what kind of object do we end up with for homology? Well, we end up with a finite or infinite commutative group. So typically we might get, for example, we might get that the homology is 0. That means just the 0 group. Or maybe we'll get the integers, the basic infinite cyclic group. Or maybe we might get z plus z, or higher sums of z's. Or we could possibly get other things too. We know from our classification of finite commutative groups and infinite commutative groups that there are these sort of infinite cyclic ones, but there are also finite cyclic groups that can appear in a general commutative group. And that will occur for some spaces. All right, so this is all for H1. The whole story is repeated at every stage. So not only can we do this at H1, we can also do it at H0, or at H2, or at H3. So it's really the same story at in every dimension. So the nth homology group is the quotient of the nth space of cycles divided by the nth boundaries. All right, so this is all rather abstract. So what we want to do today is try to pin it down a little bit by making it more concrete by looking at some very specific examples and computing what we actually get. We're going to make some computations to make it sort of flesh it out, because at this level it's perhaps too abstract to get a good sense of what's going on. All right, so we're going to look at some examples. Okay, so the first example is probably the simplest one, perhaps, the most natural. We are going to consider a circle. Let's compute the homology of a circle. Well, the first step is to sort of get around the roundness of this, because our whole approach to homology is in terms of simplices, triangles, line segments, tetrahedrons, and things like that. So we want to replace the circle with something homeomorphic to it, which fits inside of our simplicial complex orientation. Okay. So the circle is homeomorphic to, well, a triangle. So we can replace the circle with a triangle. Okay, homeomorphically it's the same, and that sort of fits inside of our simplicial complex, so we can compute with it. Okay, so what exactly is a triangle here? Well, what are we talking about? Are we talking about the solid triangle with the interior included? No, we're not. So we just want a kind of a skeleton of a triangle. In other words, we really want 3 line segments. All right, so our triangle is made up of 3 line segments. And in terms of simplices, let's give them some labels so we can talk about them. Let's call, first of all, the vertices x, y, and z. And then the simplices that we're going to be using are just 1 simplices. So we have 3 1 simplices, which are just line segments. And we'll give them an orientation while we're at it. So maybe we'll call this one A, and this one B, and this one C, and we'll orient them in that direction there. And so how we specify that? We'll write A is equal to the simplex x, y. So that ordering sort of tells us that we're going from x to y. And B is equal to y, z, and C equals z to x. So the actual object x, if we had to write it out as a set, it would consist of the three simplices A, B, and C, together with all subsimplices, namely the vertices x, y, and z. So those are all the simplices that are appearing in this story. Some one-dimensional ones and some zero-dimensional ones. All right, so let's write down what these chain groups look like. So we have C0 and C1 and C2. Okay. So what is C0 going to be? Well, it's going to be Z plus Z plus Z. 3 copies of Z, because the basis consists of the 3 vertices x, y, and z. The one chains, there's also going to be a group Z plus Z plus Z with basis A, B, and C. So your typical element in C0 looks like alpha x plus beta y plus gamma z. That's your typical element in there, where alpha, beta, and gamma are integers. And your typical element in here looks like LA plus MB plus NC, where again L, M, and N are integers. So those are the chain groups. What about C2? Well, there are no two-dimensional chains in this story. We are not considering the solid triangle, so this thing is just 0. It's not going to really figure in our picture except that it's 0. Okay, now we have these boundary operators. Let's have a look at them. Okay, so the simplest boundary operator is this D0, which is really always the 0 map. So D0 sends everything to 0 because that's what's over here. It's just the 0 group. Okay, so we might just mention it. D0 is the 0 map. It sends A, B, X, Y, and Z. X, Y, and Z all to 0. What about the first boundary operator, del1? How does it act on the generators, A, B, and C? Well, it sends A to the difference y minus x. It sends B to z minus y, and C to x minus z. And del2, well, del2 is just taking 0 to 0, so it just sends 0 to 0. Okay, so now in order to compute homology, we've got the boundary operators all laid out for us. We need to compute at every point, we need to compute a space of cycles and the space of boundaries, and then we need to take a quotient. So we need to do that here, 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 everywhere in the chain. Okay, it's going to be pretty well trivial outside here and here. So these are really the only ones that are going to figure. So let's see if we can calculate some of these groups. So let's look at C0 first. So let's look at Z0. Those are the cycles in C0. That's the kernel of this del 0. Well, that's the 0 map, so everything gets sent to 0. That's all of C0. Everything gets sent to 0. What about the boundaries? So the boundary B0 is the image of the del 1. So it's what we get from the images of the boundary 1 higher. So we know that A gets sent to y minus x, B gets sent to z minus y, and C gets sent to x minus z. So the boundary B0 is the subgroup of C0 generated by y minus x, z minus y, and x minus z. Okay. So it's generated by y minus x, z minus y, and x minus z. So Z0 was all of C0, which was just the space, the whole group generated by x, y, and z. So we see that this actually is really a subgroup of Z0. And we want to get a sense, well, what's the quotient? All right, so the question is, what is H0, which is by definition Z0 mod B0? So it's the group generated by x, y, z, mod the subgroup generated by the relations, or by the elements y minus x, z minus y, and x minus z. Well, one way of thinking about what a quotient is that you're setting these elements to 0. You're thinking of these elements as being 0 in the group. Okay? So taking a quotient by B0 is a lot like setting the elements in B0 to 0. Setting the elements of B0 to 0. Thinking of them as effectively 0. It's like what we do when we work mod 3. What we're really doing is we're setting all the multiples of 3 to 0. We're saying that 3 is 0, 6 is 0, 9 is 0. All the multiples of 3 are effectively 0. Okay, so what happens here if we do that? Well, if we set all these things equal to 0, it means that effectively y minus x is 0. So that means that essentially y is equal to x. And if z minus y is equal to 0, well, that means that z is basically equal to y. So in other words, basically, x equals y equals z. So it means that there's really only one degree of freedom in what's remaining. So the quotient, H0, becomes just a copy of the infinite cyclic group. Because every element is of the form nx plus b, 0. In other words, if you look at the cosets of B0, they're what you get when you take B0 and you add some element. But whether we add x or we add y to B0 is the same because mod B0, y, and x are the same. Similarly, whether we add x or whether we add z, it's the same. So really, the only possibilities are adding n, or some multiple of x to B0, and that fills out all of the cosets. Another way of thinking about it is that this is really a Z3, if you like Z plus Z plus Z, mod a Z2. Because this is really a two-dimensional group here, B0. It looks like it has 3 generators, but it doesn't really have 3 generators because this one is just a combination of these two. And so this is really, as a group, it's really isomorphic to Z plus Z. So this is a little bit vague because it's not entirely clear how this Z plus Z sits inside here, but you get the idea that we've got some group with 3 generators and we're modding out by a group of 2 generators. We, in this case, get a group of 1 generator Z. Okay, let's have a look at the H1. I think I'll go here. How about H1 which is Z1 mod B1. So we have to calculate the kernel of delta 1, del 1, and the image of del 2. So if we come back here to this picture here, now we're looking inside here. And let's write down what Z1 is. It's the kernel of del 1. Okay. Well, which combinations of A, B, and C get sent to 0 under the boundary map? We can calculate that by computing the boundary, say, of a typical combination, say, let's say LA plus MB plus NC. There's a typical one chain. What's the boundary of that? Well, it's going to be L times y minus x plus m times z minus y plus n times x minus z. And what is that? That's going to be, how many x's do we have? We have n minus l x's and L minus M y's and M minus N z's. Okay, and we're supposing that this is 0. So if it's 0, what are the possibilities for L, M, and N? Well, the only possibility is that N equals L, and also L has to equal M, and M has to equal N. So we conclude that L equals M equals N. And that's telling us that the kernel is all multiples of, so kernel of del 1 equals all multiples of A plus B plus C. A plus B plus C satisfies this condition. All the coefficients are equal, and all the multiples of this satisfy that condition. So that's our space of cycles, Z1. And we see that it's, as a group, it's just an infinite cyclic group generated by one element, A plus B plus C. And that's geometrically obvious because we're saying that the cycles in this graph are just combinations of this loop. What is A plus B plus C? It's just A plus B plus C. It's just that little loop going around the hole once. That is a cycle. That's what a cycle ought to be. And our algebra is just reflecting that. So any combination or any multiple of that cycle is a cycle. That's the space of cycles. Okay, and now what about the other half of the story? What's coming from the next higher dimension down? So B1 is the image of delta 2. Well, we said that this is 0. There are no two cells. So the image of this map is just 0. There's nothing in here, so this is just 0. So the homology H1, which is, by definition, the cycles mod the boundaries, is the same as just the cycles. Because if you mod out by the 0 group, you're not changing anything. So if you like, it's Z1 mod 0, which is the same as Z1, which is Z. The infinite cyclic group. So what is our conclusion? our conclusion is that, therefore, H0 of the circle is the group Z, and H1 of the circle is the group Z. Could there be any higher homology in higher dimensions? Well, all the chain groups are 0. So any subgroups of them are 0. So any quotients of subgroups are 0. So all the higher homology groups are necessarily 0. So Hn of S1 equals 0 for n bigger than or equal to 2.
What is the H0 measure?
Okay, so the question is, what does H0 measure? That's a very natural question. So the H0 is measuring the connectivity of the space. Okay? The fact that this thing has one component. Because when we compute H0, what we are doing is we're just taking the boundaries of edges. We're setting the, we're looking at things which, well, everything is H0 here. Everything is sent to 0, so everything is in as a cycle. But what is a boundary? Well, a boundary is just the image of all the edges. In other words, the difference between final and initial segments, final and initial endpoints of every edge. So the boundary always consists of things like y minus x plus z minus y plus x minus z. And when you mod out by that, you're basically equating all of the vertices. It's an important point, so I'll write that down. So the question is, what does H0x of x measure? And the answer is, it measures the number of connected components. So suppose that our space X was more complicated, but it had all kinds of various pieces and so on and so forth, but it was all connected. It was all connected. And had vertices, say, x1, x2, up to xn. If it's all connected, then when we look at C0, and we look at the cycles, first of all, well, the cycles will just be all of C0 because that's the kernel of del 0. It's the 0 map. The question is, what is the boundary? The image. So B0, which is the image of del 1, that's going to be the span of all the images of the various edges. So if you have an edge like this, A, then the edge A is going to be something like x2 minus x1. It's going to give you that as its boundary. While the next edge B is, say, going to give you x3 minus x2. And so when you mod out by this subgroup B0, what you're doing is you're equating all of these expressions to 0. So equating all the elements of B0 to basically 0 means that basically you're identifying all of the vertices. You're basically setting all the vertices equal to each other. Or maybe, so say to x1. In other words, you're basically introducing the following equation. x1 equals x2 equals all the way up to xn. And that relation inside the space the group generated by x1 up to xn, has a quotient which just consists of all multiples of x1. So the quotient is just all multiples of x1. In other words, a single copy of z. So whenever you have a connected space, the zeroth homology will always be z. If you happen to have a connected space with, say, two components, let's say this, okay? So maybe this would have edge x, vertices x1, x2, x3, x4, edges A and B. It's a connected space. We can still ask what is its homology. Well, now the image of del 1 is going to be spanned by x2 minus x1 and x4 minus x3, because that's the boundary of A and that's the boundary of B. So when you take the group Z plus Z plus Z plus Z spanned by x1, x2, x3, and x4, and you mod out by the group generated by x1, x2 minus x1 and x4 minus x3, then what you get is just two copies of Z. One for each component. So basically all the vertices in this component are identified, and all the vertices in this component identified, and the typical element looks like alpha x1 plus beta x3, say. So that's what H0 measures, and we expect H0 then to be Z whenever we have a connected space. All right, so our second example, a small variant, we're going to move from the circle to the disk. So the disk is a circle together with its interior. And as a simplex, that's a triangle, but now actually a two simplex, a triangle, a solid triangle. All right, if we use the same notation as before, x, y, z, a, b, c, then the only difference really happens with the two cell. So our chains, zero-dimensional chains, are still spanned by x, y, and z. Our one-dimensional chains are still spanned by A, B, and C. And now we have a two-dimensional cell, only one of them, and we should give it a name and an orientation. So let's call it A, capital A, say. And let's orient it so that it's sort of compatible with what we've got going here. So let's orient it this way. So in terms of the orientation, I'm saying that A is equal to the simplex x, y, z. So del 1, del 2, del 3. This part is exactly the same as before, same as for the circle. The only thing that's new now is that, sorry, this is C0, del 0, del 1. That's C1, that's C2, del 2. The only thing that's new now is that we have this two-cell, two-dimensional chain whose boundary will actually be something. So the first homology could possibly change. Okay, what did we compute the kernel of delta 1 to be? So when we apply the boundary of A, remember we got y minus x and so on. So the kernel of delta 1 was A plus B plus C. That was the group that we're calling Z1, the group of cycles, of 1 cycles. Now the image of delta 2 is not necessarily going to be 0. In fact, it's not going to be 0. So we have to look, what is the boundary of A? Well, A is a 2-cell, and it's given by x, y, z. And the way that the boundary operator works, I remind you, is we remove the first entry and write down what we have left, y, z. And then we remove the second entry with a minus sign and write down what's left. And then remove the next one and with a plus sign. So it's yz minus xz plus xy, that combination. And in terms of A, B, and C, that is the yz was B, the xz is minus C, so this is actually plus C. And the xy was A. So it's the same as the kernel. So that means that the first homology, which is the cycles mod the boundaries, is no longer z over 0, it's basically z over z. It's the group generated by A plus B plus C mod the group generated by A plus B plus C. In other words, the same group. And so the quotient is the 0 group. So the homology for the disk is H0 of D is Z, H1 of D is 0, and all the higher homologies, Hn of Z, are also 0. So what about H2? We should also talk about that. That's Z2, the two cycles over the two boundaries. Okay. So we have to look here and say, well, which elements in here are going to 0? That's the first question. That establishes what are the cycles. And we should also ask which elements from the next chain, which is actually 0, are going to be sent, what's the image of those ones? Well, what is Z2? What is the kernel of this del 2? The del 2 operator is acting on this group that has one generator, A. What does the boundary do to A? Well, we've seen that the boundary of A is A plus B plus C. So the boundary operator at this level sends capital A to A plus B plus C. So what is the kernel of this map? This is a group generated by A. All the elements here are just multiples of A. So the only thing that's sent to 0 will be the 0 multiple. Because there's only one generator, and that's getting sent to something non-zero. So the only way to get something sent to 0 is to take the 0 multiple. So in other words, the kernel is just 0. And the image of the 0 thing is also 0. So we're getting 0 over 0. This is a quotient of groups, not arithmetic. So we get 0. Maybe I should write it like this: the 0 group mod the 0 group. It's also 0. Okay, next time we'll have a look at some more sophisticated examples of homology. We'll go up in dimension a little bit, and we'll see that we're going to have to talk a little bit about what the nature of simplicial complexes and how we frame the objects that we're considering to make homology computationally a little bit more accessible. Otherwise, these things could easily blow out if you have simplices, too many simplices, simply put. All right, so I'll see you then.